Catlett is a senior computer scientist at Argonne National Laboratory. He's also a senior fellow at the Argonne University of Chicago Computation Institute and a senior fellow at the Harris School of Public Policy at University of Chicago. He's also a visiting artist at the School of the Art Institute of Chicago. Maybe he can tell us something about his artist part of him, besides the engineering part of him. Okay. Now, Charlie is the founding father of the Urban Center for Computation and Data, which is an interdisciplinary center that brings the architects, technologists together, okay, to do system design, resilient operation of cities. Now, he leads the NSF-funded Array of Things project. He establishing a network of 500 Argonne developed intelligent sensor units in Chicago. Now, before joining Argonne in 2000, Charlie served as the Chief Technology Officer of the National Center for Supercomputing Application. It's called NCSA, at the University of Illinois in Urbana. Now, he's actually involved in the development of a brainchild project of what we call internet nowadays. So he's heavily involved in the development, and he is also the driving force for the NCSA's Mosaic web browser. Okay? It is a web server infrastructure. Okay? So in 1990 to 2004, he directed the design and employment of iWire, a dedicated fiber optic network funded by the state of Illinois, which connects research institutions in the Chicago area and demonstrate Illinois to support advanced research and education. For Charlie's achievement, so he's been named by the Government Technology Magazine as one of the 25 doers, dreamers, and drivers of 2016. So, with such rich knowledge and practical experience, it is my pleasure to introduce to you Charlie Catlett. Okay.
Thanks for that introduction. So the short story is I have done supercomputing and networking systems for almost 30 years. And about 5 years ago, we had a new mayor come into the city of Chicago, Rahm Emanuel. And we'd been doing some discussions with the city before that time, looking for areas where our research might address some challenges that cities like Chicago have. And it was when Rahm Emanuel came in that he brought in a new class of commissioners who wanted to innovate and to use the city as a place to look for, well, to innovate, and who were willing to take some risks. I've heard a number of people say some version of the statement that cities love to be, and mayors in particular, love to be the first to be second. So mayors are not judged by their innovation, but by stable services. And so when Mayor Emanuel came in, then we began sitting down. I had opportunity to do a sort of a local sabbatical, if you will, for a couple of years. And so I decided I'll just try to figure out where are the interesting computer science research projects that overlap with city challenges. So I began to meet with commissioners in the city of Chicago and deputy commissioners and ask them what their challenges were without offering any technology or shiny tools or toys, but just to find out from them what their challenges were. And early on, one of the things that sort of shaped my thinking about working with the city of Chicago was that I learned the mayor was looking for, on a neighborhood level, and Chicago has something like 70 neighborhood areas, he wanted to have some sort of mathematical indicator for a neighborhood that would tell him if he needed to intervene in some way from a social science point of view or economics or public safety. And the idea of classifying the state and direction that a neighborhood was going was intriguing to me from a computer science point of view. And so that kind of got some of our work started. Today I want to talk about 3 different areas that we're working in and try to give you a quick tour of what's happening with our work in Chicago and how it's begun to put us in contact with other cities as well. Then I guess maybe a little bit of background on Argonne National Laboratory and the University of Chicago. So you know about the University of Chicago. We're about 7 miles, about 10 kilometers south of the city center within the city. Argonne National Laboratory is a Department of Energy science laboratory. It's about 25 miles outside of town. And so I spend my time between Argonne, University of Chicago, and then we also have offices right down in the city. So we have 3 places where we've got people working. Urban Center for Computation and Data really was not so much about building a traditional center, but building a collaborative network among scientists at the university, at the laboratory, community organizations and civic planning organizations. And as was mentioned, I am a visiting artist at the School of the Art Institute of Chicago, which is much less glamorous than it sounds. They just didn't have a position called visiting engineer, or that's what I would be. So I took the visiting artist and wear that, carry my badge proudly. But there I work with the interior architecture and design objects group mostly. And we do a lot of sensing projects and urban design projects. One that we're doing right now is along a new conversion of an elevated train to a park. And we're doing a lighting system that these architects have designed a lighting system for a bridge. And we're going to do that lighting system and have it controlled by air quality. So Luis mentioned that he and I had I would say privilege last year of working with the President's Council of Advisors on Science and Technology to try to answer the question in the course of about 1 million phone calls, well, actually of weekly or biweekly, so semi-weekly in some cases, phone calls. What could the federal government in the United States do to help U.S. cities to deal with various kinds of changes over the next 50 to 80 years? Technological changes in society and the demographics of society, changes in climate and technology. And one of the things that I was really happy about in this report was that we ended up with this notion that cities are not just these infrastructure things, and they're not just social things, and they're not just sustainability things, but they're really a mix of different kinds of infrastructure and activity. And if we wanted to have an impact on energy or transportation or health or buildings, we needed to look across multiple of those areas and to really look for solutions that would address challenges across these vertically and not just focus on one, perhaps at making the other two, causing problems the other two. Now, you've probably heard of the Rockefeller 100 Resilient Cities Project, and Chicago's one of those. We had about 100 people in the room in September to assess the city of Chicago, and by people I mean there were people from, a small number of us from universities and labs. Mostly they were community organizers and people that work for the city and residents of the city, business leaders. And the Rockefeller 100 project uses this city resilience framework to just kind of get an assessment of how the city's doing from a resilience point of view. I found it sort of instructive because I come from a national laboratory where we do environment and engineering. And so I think of resilience in terms of infrastructure and environment. But this is a much broader picture of resilience. And one of the things that those 100 people did in that room that day in September was we broke into groups of 10 or 12 people and were asked to assess in each of these 12 areas, how is the city of Chicago doing? And then we sort of aggregated those into a red for not doing well, yellow for, could do a lot better, and green for doing pretty well. And this is how it turned out for Chicago. And every city would be different, but it turns out we're doing pretty well in the areas that I think of as resilience, but we're not doing so well in some of these other areas. And so that caused me to think a little bit, maybe to take a step back about resilience and think more broadly about what that means for cities. But it also reinforced some of the work that we'd already been doing with helping the city and the scientists at the university and other places use data that the city has. And I just want to show you a couple of maps here that kind of illustrate one of the things we're interested in, which is to understand how different conditions across the city affect people's lives. So here on the left-hand side, this is life expectancy in Chicago. The difference in life expectancy between dark red and light yellow is 14.6 years. The difference in Philadelphia here at the bottom between some neighborhoods and the sort of worst and the best neighborhoods is more like 20 years. And then asthma, you see this similar thing, these parts of the city that are struggling with health conditions like asthma, and similarly here in Boston. And then there are infrastructure issues. Here's a color-coded map of the city of Chicago. And if you live in one of these green areas here, then it'll take you 30 minutes or less to get to the central business district, to the Loop. If you, on the other hand, live in some of these gray areas here, it'll take you at least 90 minutes. So where you live in the city also affects and you can see this if I were to show a unemployment map or a crime map, it would look a lot like this with these dark areas like you see there. So when we were doing predictive analytics like this with the city of Chicago, and I've got a couple of examples of what we've done there, but it was when we started to do this crime prediction project that I started to really get excited about the notion of putting sensors throughout the city. This is a predictive project that is now it's a spin-off company working with police departments around the U.S. The idea is that each of these are census tracts for the city of Chicago, 866 different ones. We took a decade or so of crime data, and we tried to develop a very simple predictive model for each of these over the course of between 1 and 72 hours. And you can slide that slider across the top to get that. With the idea that we would predict on an hour-by-hour basis the likelihood relative to the mean across the city where we're likely to see crimes happen in the next 1, 2 to 72 hours, as a tool to help the police department know how they should patrol their areas. So it's a tool that the City of Chicago has something actually more sophisticated than this that they're using, and I worked with their former Chief Data Officer, Brett Goldstein, on this project here. But what we really wanted to do was to figure out what is the relationship between our predictive algorithms of crime here and changes in weather. In other words, if we add weather to the equation to predict each of these changes in weather, does the prediction get better? It turns out that it does. But while we had each of the crimes that took place here right down to the street address, latitude and longitude, we had only a half dozen weather stations around the city. So we don't have enough data really to do the experiment we wanted to do. I know others have done, at Harvard and places like that, have done research similarly looking at air quality and people's decision capabilities and air quality and crime. And the air quality picture for the city of Chicago, like any other city, is also a sparse network with not enough spatial or temporal resolution. So I'm going to come back to that in terms of why we ended up with the Array of Things project. But as I mentioned, I wanted to talk about 3 different areas of work that we're doing. So the first is computational modeling, to look at how we might take existing computational models for components of cities and plug them together. It's a very exploratory effort that's funded by the Department of Energy as a 3-year project with 5 laboratories involved, including Argonne. And I'll use this as an illustration. So the other two areas I'll talk about is the data analytics infrastructure and making data more accessible to scientists. And the third will be putting technology directly into the city with the Array of Things project. Here we just took 4 models where we had existing models for the city. We have very good transportation models like you saw this morning, these agent-based models. We have another social economic model that has 3 million agents for the city of Chicago and looks at social economic decisions. The Department of Energy has a very robust building energy demand modeling system called Energy Plus. And then there are a number of different large eddy simulations that look at urban atmosphere, but always at the kilometer or larger scale. And we want to go to, obviously, a much finer scale using something called NEC 5000, which comes from Argonne. So our project is not so much about pushing these individual models, but asking the question, what are these things exchanged in order for the building energy forecast to be better? What does it need from the urban atmosphere model? That's actually where we're starting from here. And where does the data come from different things? And what you see at the bottom is really 3 different types of data that we tend to look at and need to deal with. One is this open data, and I'll talk a little bit about that with a system that we've built called Planario. Another is sensor data, like we're going to get from the Array of Things, and I'll also want to try to make it clear where we're at on that project. We don't have 500 sensors yet, but we have a 2-year window to put them in. And then something that we're just starting to look at, which is how to enable people to share protected data, because typically the way, and by protected data I mean things like health records or education records or social services records, crime data about individuals. And those are typically, a single researcher at a university has their data set from Chicago Public Schools and they don't share it with anyone else, and they don't have the ability to take that data and put it together with corrections data or crime data that's of a sensitive nature. So we're starting to look at how we can create a system that allows those data sets to be shared. Now, in this specific model for these couple models, we chose to just start with the large eddy simulation and a building energy model and look at what are the flows between these two, and then how do we start to set up a physical model, a 3-dimensional model for how the building interacts with the environment. And then to look at actual buildings in the city of Chicago. This is the Chicago Loop right here. It's named the Loop because there's an elevated track that is a loop around this area. But it's about a square mile, and so we said, let's start with maybe 4 square blocks here. We chose these 4 square blocks. As Luis knows, this is the building that's owned by the MacArthur Foundation, which provides funding to Luis and ourselves. And we thought, well, we should start with the building of people who give us funding. But this part of the city here, this is the federal court building. This is another federal building, as is this one here. This one, by the way, is the building where I once visited a young congressman named Barack Obama. His office was right in that building. He wasn't there, but I talked to his staff. And so let's take this 4-block area and let's just look at how we might translate the information we've got about buildings into a 3-dimensional surface like this one, and then get measurement data by putting these Array of Things nodes on rooftops and on the corners, and then translate these into geometries that can be used that would feed into the air and heat flow simulations. And those, by the way, the Array of Things nodes would be particularly relevant here to look at. They have cameras that look straight up along with infrared and ultraviolet, so they would give us some information about solar load on the side of these buildings. And ultimately, we want to be able to do something like you see here for a couple of buildings where we're looking at the air and the heat flow in between those buildings, but not on this is a single block right here, not just on a single block, but on an entire city. And not just on the 500 buildings that are in the Chicago Central Loop, but the 600,000 to 800,000 buildings, depending on how you count them, throughout the city like Chicago. So that's, as I mentioned, that's a project that's just beginning, and we're looking at how we can create a framework so that any model can be plugged in with another model and exchange the data between them. So let me take and go sort of through these 3 areas here: open data, sense data, and protected data. And in terms of open data, we began also a couple years ago, and I had conversations not just with the city, but with scientists at the University of Chicago that were doing social science or economics. And I found over and over again that there were lots of people playing with open data in the city, computer scientists mostly, but social scientists and economists, people that really had questions about cities, didn't really, they in some cases weren't aware of the open data. In other cases, they were like, well, we know there's open data there, but we don't know how to get to it or how to find interesting data, and we don't have time to go and pour through, file by file on what's on the open data portal. So we began to think about how do we present data to these scientists in a way that reduces the amount of overhead from them having a question and then finding the data and answering that question. And I mentioned that there were a lot of groups doing things like this. This is a color-coded footprint of all the buildings. This is zoning. This is a snapshot from an animation of 2 days of these red dots are snowplows. In blue are the snowplow drops a blue dot every time it goes through a part of the city. So of a 2-day blizzard, there's an animation of all those snowplows. And some of this is useful. We were able to use GPS tracking like this of garbage trucks to determine and give the city feedback on whether a new routing scheme for garbage pickup was better or worse for congestion and use of, how many miles each truck drove and how many miles they were sitting idling with their diesel engines. But ultimately what we found was that commissioners in the city of Chicago, and I think other places as well, are not just wanting to do maps of data, but they're wanting to ask questions like, how can we improve our use of resources? And oftentimes those end up being predictive analytics problems. So to illustrate that, this is a 60-day trial that we did after the health commissioner came to the chief data officer and said, I have 32 inspectors who every year have to inspect 15,000 food establishments. So that's 500 inspections per inspector per year. And the way they normally do it is just random. So they're looking for a way to more rapidly catch violations so that they can fix those violations. And the very first thing that we did was to say, well, why don't we take previous inspections and other data and do a model that just gives us a ranking of high or medium or low risk of a violation. And then send the inspectors out looking at the high-risk places first. But this is as I said, a 60-day trial where half of the inspectors, this red line, is the number of violations found over the number of inspections. Half of the inspectors did the random inspection. The other half were given a list, and they said, "Why are you giving us this list?" And the commissioner said, "We can't tell you, but trust us and just go do them in this order." And they did, and what they found was this simple rank ordering gave about 7.4 days on average lead time where violations are found before the random would find them. It doesn't sound like a lot of time, but in a 7-day period, a lot of food goes through an establishment. A lot of people eat in a restaurant or buy food from the grocery store. Now we have a group of applied mathematicians at Argonne that are trying to push this curve up as high as possible here by now just the traveling, not the traveling salesman problem, but the traveling inspector problem. So looking at different ways to optimize. And that's just an example of the many different types of optimization that cities are interested in doing. Now, as I mentioned, most of the people at the University of Chicago studying cities like Chicago aren't data scientists, and they are looking for ways to find data relevant to their question and then bring it down and analyze it. So we built a system called Planario that allows you to look at a city and hear and say, I'm interested in this part of the city. This is the part of the city around the University of Chicago. And maybe I'm interested in just this calendar year, and I want to know what data is available. Because I'm looking at food safety, maybe is my illustration here. So I just draw this and I do a query, and I find that there's counting up here that there's, 20 or 30 or 40, so 27 different data sets that are available about that area. And they span lots of different parts of the city. So I get a little bit of a signal here that says, what's the temporal signal look like? I want to look like, how does that set of, in this case, food safety inspections, how does it look across the area that I'm interested in? I'm going to change to 100-meter resolution, and so you can see the dark blue are 7 or more food safety inspections. These are not violations, but inspections. But I'm very interested in this particular hypothetical here. I'm interested in which of those inspections were triggered by a complaint. So since my system has pulled the data in and knows its structure, I'm going to put a filter on here. And then, of course, that's going to be, ideally, it's going to be a lot less than this one here, and it turns out it is. So you have a couple of different ones where you have 2, and most of them are just 1. So I'll zoom in a little bit. But now I've got this data that's interesting to me because I wanted to study food safety in this part of the city, and then I can download it in a variety of different ways and then go off and do my analysis. So we actually built this as a sort of a back-end geospatial database. We made it in such a way that it was easy for anyone with a URL to data to put that URL in, help us by telling us which of the fields are the time and date and which of them are location, and then integrate that data into the system. So it's a back-end database with APIs that we use to produce what I just demonstrated. The city of Chicago then funded us to support those APIs and support their work to do a different front end, if you will, than what we did. But this one here is aimed at residents of the city who might want to know about 311 service requests for their area and service, food inspections or what have you. So this is, I bring this up to illustrate that every project that we do with the city of Chicago, we're asking the question, can another city take what we've done and repurpose it for their city? And can the city of Chicago build other things on top of what we're doing? And this we thought was a very good success story. This is called Open Grid. We put this into the Amazon Web Services marketplace, so it's something that a city could go in and with a click pull this down and use it locally. Now, I already showed this before, but I want to bring this up because this is yet another use of the APIs of the backend Planario, where we use this as the engine for the predictive analytics project. So that's open data. I want to talk just briefly about protected data and another project that we're just now starting to do with the U.S. Census Bureau. And that is to say, how do we make it so that different federal agencies can safely share data so that a researcher can do studies that look at census data along with corrections or crime data or social science data. That's typically data from different sources that is not shared. And so this is a technical diagram of what we're looking at doing. A bunch of screenshots, but essentially the idea behind this system, these are screenshots from a conceptual system, is to provide a environment that looks a lot like Amazon.com, where you can search for data. It remembers what data you searched for before. It connects you with data sets that other people who did this search were interested in this data set. So we're beginning to build this on top of something called the Globus Toolkit platform, to build this and to do it in such a way that as with Planario, that we're really aiming at non-data scientists, but at a normal research person that wants to look at data and wants all of the friendly tools that they get in their personal life with things like Pinterest or Facebook or Travelocity, et cetera. Okay, now the real thing I came here to talk to you about was my baby, which is the array of things. And so I want to really sort of kind of tell you our motivation behind building this, our schedule, what we're actually doing, what we're hearing from other cities about interest in the project, and where we are as far as the project timeline goes. I mentioned earlier that when we were doing the crime and weather data, we only had 6 places across the city of Chicago, which is 600 square kilometers, where we could get weather data. This is a similar picture of about 600 square kilometers of Chicago, and these little markers are the air quality monitors for EPA, the state EPA, the county, and federal. And so you can see these are tens of square miles where we have no information about air quality. So if we really want to ask the question about asthma here in this part of the city, we don't have the data to do that. So this was the first sort of idea that we had. This is now 5 years ago when we started the project, where we said, let's try to take the $1 million EPA station and shrink it in size and in cost by taking advantage of new technologies down to $1,000 or $2,000 per device, and then let's see if we can get the support from the city and the federal government to put an instrument across the whole city. And as we did that, we started having workshops now about 3.5 years ago with different science communities and asking them the question, if for your research you could put a measurement across the city, you could put 100 sensors or 500 sensors, what is it that you would want to measure? And every sensor that's in the Array of Things project came out of these sort of discussions. We actually also found, especially from some of these social science discussions and the engineering discussions, that there was interest in what I've been calling digital observation, computer observation, which is to say, if you're a social scientist, we have a conversation with social scientists more and more lately where I'm saying, if you could stand on the corner with a clipboard for 24 hours a day for 6 months and observe, what would be the things you'd be looking for? Maybe you'd be looking for sound or imagery. Maybe you'd be looking for the number of people walking babies through the park or the number of bicyclists wearing helmets. And we want to translate those questions into computer vision and computer listening capabilities. We talked to the transportation people. They wanted to go beyond just observing the traffic flow and the pedestrian flow to the point where they would be able to control infrastructure in real time. And some folks are already doing this. Carnegie Mellon has a really nice test bed with 50 intersections that they're using. But what we wanted to create here was a sensor network, but also an infrastructure on top of which these scientists, computer scientists and others, could build and do experiments in a real city like Chicago. So we had to design a system that would not just report data, but also would provide computing right down on the street corner. Now, one of the things that I'll illustrate this with the Vision Zero. Vision Zero, these are some of the cities, there are others as well, that have this initiative that is an initiative to eliminate traffic-related fatalities by a certain point in time. In Chicago, the Vision Zero initiative is to eliminate traffic-related fatalities by the year 2022. That's about 150 people a year that are killed in various kinds of traffic accidents. In any safety program, it's good to know where the accidents happened, that people were killed, and analyze that. And we've done analysis of those various factors involved in those accidents. If people are driving too fast, if they're driving, having drunk alcohol, if they're wearing helmet or safety gear. But what you really want in any safety program is to know about near misses. So imagine that you could program a device on the corner that looks for a near miss that you would not catch otherwise. It looks for a car that suddenly swerves or a car that comes to a screech with a pedestrian right in front of them. And these are the kind of things that we've heard from the science community that they want to be able to experiment with in a real city, in a real environment. Now, the computer vision people are not just the urban people. Of course, you want to use computer vision to look at the pedestrian flow here or to pick out the vehicles. But we also found other interests in the city of Chicago. There are many, like other cities, many areas that flood. And so we were meeting with the Chicago Community Trust, one of the foundations, before we decided to put a camera on the device. And they said, can you tell us if there's flooding? And we thought about it, and we said, well, yeah, we could put sensors out there for water flow and things like that. It'd be very expensive to maintain and to put out there. Or we could put a camera and do image processing. And, of course, we went with the camera. There's a Chicago Forest Preserve, Cook County Forest Preserve, is interested in the sound that a particular frog makes just once a year. So the folks that study frogs are interested in putting a microphone out there so they don't have to sit out there and listen for that frog making their noise once a year. We have a privacy policy associated with the cameras that we don't show the images. We'll change it so we can show images that don't have personal information, but that's why this is a stylized image from one of the cameras. You can see the amount of intersection that we cover. Some of the cameras are landscape and some of them are portrait. But we're doing image processing on the platform so that we can extract information from those images, and then working with folks like Juan Bello from NYU to look at computer listening as well. So I want to maybe go through a couple of, I would say, lessons learned for software people like ourselves in building hardware. I'm just going to check my time here. And the first was, we had done lots of experiments. I have probably 40 sensors in my house. I have Arduinos and I have particle, photons and Raspberry Pis all over my house. And I find it's pretty easy for me to put a Raspberry Pi in my basement and monitor. I have got a sump pump that keeps the basement from flooding, the water heater and the furnace. And I can graph how those are running over a period of time. I actually found that my sump pump went out by watching those numbers, and I get a text message if it goes off more than 7 times in 30 minutes, which was my heuristic for I should pay attention to my sump pump. But those are pretty easy to build, and when you look at sensor networks and Internet of Things, they are typically fairly straightforward and not hard to build. And they typically look like this. This is, in fact, a board that our guys designed with a bunch of different environmental sensors like barometric pressure and temperature and humidity, vibration, magnetic field. And this board has a very cheap and very reliable processor on it. And then you put it together with a modem and you send that data up to some server somewhere. And, this is sort of like a weekend project for a graduate student to do a sensor network like this. And you can keep it very reliable. Even, our goal was that it should be able to run untouched for 2 years, or at least not physically touched where we could log in and fix a problem with it. So whereas this is a pretty straightforward thing to design, the minute that we began thinking about computing down on the desk or on the street corner out in the elements, it got way harder. Because that meant we didn't want to introduce something that the science community wouldn't use. And the science community uses things like OpenCV, computer vision library, or the Berkeley Cafe deep learning platform. But the point is they use Linux, the computer science community. So we had to put Linux devices in. For those of you, I think, which is all of us, with laptops, you know that no matter what you do, even if you try not to make any changes, your laptop is not going to run for 2 years without a problem. So that meant that we were introducing this inherently unreliable device and then making it worse on ourselves because we're saying, we're going to download new libraries and let people program these things. And 90% of the project that we've undertaken over the last few years is really about this. It's building on a project called Waggle that we started a few years ago out at Argonne National Laboratory. And the idea was this deep space probe design where for average lifetime of 2 to 3 years, you wouldn't have to touch the device because it'd be in a place that's impractical to get to or too expensive to get to. And we wanted to build into that platform the ability to do this computer vision and listening, by the way, but also a strategy by which we could introduce new sensors as they come out from the research community and take advantage of lower cost and more capable CPUs. And just to illustrate that last point, here's the CPU that's in the box that we're deploying right now, which is not that different in terms of capability than this one here from our IBM Blue Gene P that we put in 2007, and this IBM Blue Gene Q that we put out in 2011. Now, of course, the Blue Gene has hundreds of thousands of these, and we only have 2 of these in each of our devices, but the technology for processing keeps getting better and better, and if you think about this one here actually has a GPU as well. So to just rely on the cloud rather than compute down on the street corner eliminates a lot of interesting research, but also capability that you want to do. And so we wanted to be able to take advantage of that. And what that meant was that we had to build a resilient system and not treat these as the resilient backbone. So these 2 Linux devices are actually controlled by this board that we designed. This is actually one of the early versions. We've changed the layout a little bit. But it's got relays on it because it can control the power to these. It's got current sensors, for example, to, if a CPU is starting to go bad, it starts to pull more power, and so we can detect that. There are things like heartbeat monitors that we watch for, and as I said before, a very reliable, low-cost control processor, real-time clocks, and some other things that I haven't pointed out on here. But what this allows us to do is if we have a problem on one of these, this is able to restore it to some known state. We also chose these here because we had the sort of, I would say, intuition that putting a standard SD card, which you have in a Raspberry Pi or any of these do-it-yourself devices, putting one of those SD cards out in the Chicago weather and having it get down to, way below freezing or very hot in the summer, eventually it was going to go bad. So we actually chose these devices because in addition to the SD card slot, they have another eMMC memory slot in the bottom. So we have two physically distinct storage. That means that the SD card can go bad and we can still have a node that's working. Now, this ability to kind of bootstrap back and forth, we just last week were able to take advantage of that and validate our assumptions about the SD card. So it turned out SD cards are really good for moving a bunch of JPEG images from a camera or to a camera. They're not so good if you have dozens of processes on a Linux device, each wanting to update files and keep files open for logging or configuration. So we were finding the SD cards in operation getting corrupted, files getting corrupted, and our diagnosis was that we were essentially overflowing the cache memory storage management of the SD card. And we were able to reconfigure these by downloading to this guy new software for these so that we switched over and the eMMC is now the primary storage capability. We've had other experience in the last 6 months or so when we've had of order a dozen of these up on 20 feet up on street poles where we've been able to log in and diagnose a sensor board that's gone bad or in this case needed to reconfigure the devices. So we feel pretty optimistic that we've got a reliable infrastructure, a platform, if you will, that we can put out on the streets of Chicago. These are the current sensors. And by the way, there's a website, arrayofthings.org. You can go and get all of this detail about what's on the device. But we're looking at essentially 3 types of data that we're collecting or measuring. One, things like infrared light, visible light, magnetic field. These are just environmental. In some cases, like I'll take temperature and humidity, we've got multiple technologies that we're using just for being able to have redundancy. So it turns out temperature, of course, it's nice to know the temperature. Temperature and humidity are necessary in order to interpret some of the other sensors' output. So the carbon monoxide or hydrogen sulfide or nitrogen dioxide, the values that we get from those sensors have to be interpreted in light of things like temperature and humidity. So it turns out that these are important not just in their own right, but in order to make the other data useful. Another example, which we learned early on from talking to urban weather researchers, is that just having temperature isn't that useful either, because you don't know if you're getting a temperature from under an oak tree or out in the middle of a parking lot. And so there, although we don't need a sensor to tell us if it's light outside, having a light sensor, in fact, we also have infrared and ultraviolet, helps us interpret those temperature readings as well. And I don't know if you've poked around with some of the Internet of Things sensor networks out there, but I have found it's very difficult to interpret data from these networks that don't have a built-in strategy for the context that you need to interpret that data. As an example, and I won't name the city or the company, but a very well-respected company in sensors, air quality sensors, put a bunch of these around a U.S. city as an experiment, and I look at the data and I see that in this part of the city, it's 20 degrees Celsius, and then 2 miles away, it's 0 Celsius. So obviously, we're looking at, I don't know where those sensors are. They may be in somebody's kitchen or in their porch. So having that context is important, and it goes beyond just the context of the sensors themselves to where those sensors are located and what are the environment around those. So one is environment. The other, air quality, as I mentioned. We're also using a particle sensor called an AlphaSense from a UK company. We're considering whether to increase that number to 50 or 100% of the nodes. This is a device that gives us not just PM 2.5 and PM 10, although that's its native capability, but we've got a version of it that, with the blessing of the company, has modified firmware, so we get a histogram of 1 to 100 microns, which is really good because you want to know that ultra fine, but you also can now start to look at pollen, which is more like 20 to 80 microns in terms of its size. So that gives us important data as well. And then the camera and the microphone, somewhere on here is a microphone, those I would classify as giving us activity data. So the flow of pedestrians or bicycles. City of Portland is going to take 3 of these next month and put them in. And what they said was, we're interested in air quality, of course, but we're also interested in what the impact on safety has been of our bike share program. So what we want to know is, can we do an image processing sort of classifier that looks at bikes as they go by and says, that's a bike share or a private bike, and is the person wearing a helmet or not? So not just what percentage of riders are wearing helmets, but what percentage of bike share riders are wearing helmets, and what percentage of private bike riders are wearing helmets. So that's the kind of thing that, as we can program these things, it's essentially a new sensor that can be put out without having to do a physical installation. So I showed you this before, the simple version up here, the Linux device that sort of throws that off. These are all of the components then that are inside the package that we're assembling and putting throughout Chicago. As I mentioned, there are about a dozen of these up. 6 new ones were delivered to the city yesterday, and we're going to start delivering 10 per week to the city until we get about 100 of them up, and then we're going to do a redesign. We've got some changes we want to make, and then our goal is to have between 200 and 300 in the city by the end of this calendar year, and then 500 by mid to late 2018, with an installation that has 3 distinct phases that allows us to put new technology into the hardware with each of those phases. And then the idea is to go back to the National Science Foundation and ask for an operational funding for multiple years, where we replace 100 to 200 of these every year, so that we have a way to insert new sensor technology. An example of that is the particle sensor that we're using is about a $400 sensor, and that's on top of about a $1,200 bill of materials for the platform itself. But there are 2 groups that we're aware of, 2 groups that have sensors that look at particles, but that would be in the $5 to $20 range, and not the size of your fist as the AlphaSense is, but more like the size of your thumb. So over time, that's the kind of improvement in sensors that we should be able to count on and then start inserting in with each of these waves of new devices. So what we've had to do then is, and this is where the School of the Art Institute came in because they worked with us on design, a couple of different aspects of design came to play here. This is the package as it is put together, and that's what it looks like up on a pole. This is at State Street in Washington in the downtown area. You can see it looks fairly large. If it's maybe 1.5 feet tall and about 1 foot wide. Looks fairly large if I were to put one on the desk there, but when you put it up 20 feet on a pole, it looks fairly small. Inside here is where we have all of the processing. So this is our resilience board here. This is one of those Odroids. There's another one underneath. And just as a note here, those aluminum blocks are, we order the Odroids, the single board computers, without heat sinks. And the reason is that there's not much room in here for air to move around, so those fins and the fan on the GPU don't really do you much good. Instead, what we do is we put, with heat tape and paste, these aluminum blocks that then are spring-loaded against the aluminum chassis, so we're doing passive heat, passive cooling, if you will, by drawing heat away from them into the aluminum chassis. So this sits behind this decorative shield here. The bottom 1/3 of this is a power conversion device. You can see we've got a wire here, so this is direct wired, standard outdoor plug-in. It can work at 220 or 110 volts. And then inside this Stevenson shield, these are essentially upside down bowls with the bottom cut out of the bowl so that you have a cavity inside here. Inside this dome is the cellular modem. Inside this dome, you can barely see that there's this lens there where there's a camera pointed out. At the top of this box is another lens that you can't see here with the upward-facing camera, infrared and ultraviolet sensors. And then inside this cavity, we hang this harness where you can see the camera here, the microphone, that sensor board that I mentioned that I showed before with the and sort of environmental sensors. Here you can see these are two enclosures that are Faraday cages to enclose the gas sensors, 7 different gases, because those sensors are electromechanical and they are very sensitive to electromagnetic interference. So we've got to put them in a Faraday cage. And then this black device here is the particle sensor. So all of that slips down into this here with this, what is then a bundled umbilical cord that goes between the two. We designed this in such a way that it would do the job it's meant to do, which is to prevent direct rain or direct sunlight from hitting these boards. It will be interesting to see how these do in other environments. Like, in Hong Kong, the rain often comes sideways, so we may have to look at the design of this as different for climates like here in Hong Kong. This passive cooling, one of the things this board does is, you can see this, barely see these black wires here. Those are thermistors, temperature sensors, inside the box. So the small $4 CPU on here will decide if it's too hot to tell the Linux devices to sleep. So it puts them to sleep, and then it wakes them back up when it's cool enough. So in a place like Delhi or Dubai, two places that we're talking about doing pilots, we're interested in how long these things will hibernate. And in Chicago, we might have an hour or two outage, across the city on a very hot day. In Dubai, it might be a 2-day outage or a 2-month outage. And so we're going to have to look at different ways to cool this as well. But in Chicago, this is what we're deploying. And all of the work that went into this, the industry design, the bending of metal, these are injection molded, bended metal here, this circuit board, all of these are done by partners in the Chicago area. We're all within an hour drive of our engineers, and that turned out to be not any more expensive than if we were to send them to, say, India or China, but a great advantage to be able to just drive across town and sit down with the partner and work out any sort of issues with the device. I thought you might want to see what it takes to put one of these together. So these are all the parts. Let's see if this works. No. I think I have to click on it. There we go. Now, we have not been able to get any of the factory workers we're working with to work this fast. So it takes about 2 hours. But one thing just in terms of lessons learned for software people anyway, this was pretty straightforward for our engineers, a PhD electrical engineer, computer scientist to put together. And the first dozen or so that went out, we put these together ourselves. Our plan was to have, actually the guy that was in this picture, the design house that helped us do this design, did all the 3D models and 3D printed these early on, and they were going to assemble these, but we found that when someone else was assembling our device, there were points during the assembly process where you really needed to check to make sure everything was working. And we learned that because we took delivery of 20 of these, most of which had problems, and so our guys had to take these things apart, which is not an easy thing to do, and rework them all. So we took a step back in September. We really had hoped to get 40 to 50 of these up in Chicago by the end of last year, but we took a step back and said, let's really work on the assembly and manufacturing process to make sure we can get reliable units out. And, oh, by the way, to work with a company that can do more than just 10 per week. And we're just emerging from that process right now. We also have had to do testing. This is infrared looking at heat. We did heat studies of the insides of the box, also using infrared. we have these versions that are not packaged the same way, but all the same parts, running out in fields at Argonne and down at UChicago for the last year and a half or so. And then this is the FCC emissions, electronic emissions test facility where we ran them through a test from a few hertz to up to a few tens of gigahertz, and made sure that everything was shielded. So we didn't technically have to get FCC approval for the device, but we wanted to have a piece of paper in hand because we were afraid, and probably afraid is maybe not the right word, so we expected that somebody, when we put this up in their neighborhood, would complain that now their Wi-Fi doesn't work anymore, or their cell phone doesn't work anymore, and we needed to be able to produce this to say, well, maybe that's true, but it's not related to our device because here's the testing that says we're not emitting any electronic radiation other than the cell phone modem at the top. These are the first 40 locations. These guys here, I've met with, we were talking about governance this morning, I've met with 7 layers of management in the city of Chicago, from these guys here who work for this guy to this guy's boss and all the way up to the mayor. Actually, the mayor would be layer 8, so it's 8 layers of management, to make sure that they were all excited about the project. Because, as I was telling Luis earlier, this guy, this is Bob, so he's the foreman of these electricians. Their job is to maintain the city lights and the signal lights. And Bob, needs to be on board because he schedules his guys to do this work. The city, the mayor, and the Department of Transportation commissioner is doing this installation at no cost to the project. And that's about $1,000 per pole of labor. So it's a fairly big investment. These guys don't get any of those $1,000. It's just more work for them. So having them on board was important, and then his boss is super important, because if they're not on board, even if the mayor says this is a great project, which he does, they could stop the project. There would be problems that would cause it to be impractical. We started meeting with these guys 2 years before we first did the installation, almost exactly 2 years. This is from one of our early meetings, and this is a $2,000 3D printed version of that Stevenson shield. We were kind of afraid, because we didn't know them very well, that they might drop it or something. And when I walked into their shop, there was this big banner, like the size of this wall, across the top of their shop from when the Chicago professional hockey team had won the world championship, and there was a banner across their shop. So I said, aha, we have something in common. We love the Chicago Blackhawks. So we put this Blackhawks sticker on the device to make sure that they would treat it respectfully, and that worked very well. We also learned a lot from working with these guys in terms of electrical safety, as well as, I want to go back and talk about the design just for one moment. Aesthetics, of course, but this quick replacement was really important. It takes these guys about 2 hours to do the wiring, and to get the wire from the breaker box to the base of this pole through conduit, and then up the pole, and they have to drill a hole up here. So all that's about a 2-hour job. And we wanted to make sure once that was done and that wire is up there, that within 15 minutes they could replace that with a new one. Not just because we have to replace ones that go bad, but we want to upgrade over time. And we felt like if this was $1,000 a pole every time, we only have one shot. So what we said was, we said to the electricians, help us design this so that it's as easy to replace this as when you have to go out and replace holiday decorations like lights and things like that. And so it's got these, you can see these 2 lines there. That's a stainless steel strap that goes around the pole, and then it's a screw-in connector. So that was a really important part of the design that we worked together with the electricians on. We also worked with them on electrical safety, and they influenced some of our choices. We wanted originally to put these about 6 feet off the ground. So we thought we'll put a button, maybe some LED lights on them. And so we said to the electricians, we would like people to be able to interact with these devices. And after they stopped laughing at us, they said, we don't think you're going to get the kind of interaction you have in mind. They thought maybe you get like a baseball bat, people vandalizing them, but maybe. So they talked us into going up 22 feet. You can see this is the first one going up here in the city. The first installation here, these are the first 40. They've already wired up most of these locations. There were a few that didn't work out for one reason or another. And we've put 6 of them here. There are some others elsewhere. And then we're about to just speed up and put the rest of these in. We have now a process by which we select these locations that really is summed up by these 3 things here. Where we find a neighborhood that the residents or business owners have something they're concerned about, traffic safety, air quality, noise, flooding, that's the first thing we're looking for. The second is if we can find a group of scientists that already have funding where they would be interested in looking at the data from these things and giving some sort of insight into that challenge that the residents are concerned about. And the third necessary ingredient is that there's some commissioner or department head or deputy commissioner in the city of Chicago who's also interested in doing something about that resident concern. And where those three things are coming together, that's where we'll see successful implementations. If we just put these up, to collect data, that's a technology project. It's not going to really help the city unless there are these other factors involved. This first installation you can see along the lakefront and then east-west here. This from here to here is about 25 kilometers. So that T shape there is the atmospheric and air quality people wanting to know about lake effect. We've got this downtown to start to look at pedestrian and vehicle flow. And then this cluster of devices here in a part of the city that's got very high asthma and air quality issues and an interstate highway running down along with some factories. So that's our air quality experiment. So these first ones will help us to determine optimal placement, density, et cetera. So I'm going to close by showing you something that also surprised us, and that was that there were so many groups that were interested in getting this kind of data about their city, but didn't want to develop a platform like we had done. So we came into it as computer scientists, assuming that Pittsburgh had their own platform and other groups would want to build their own, and we found that that's really not the case. Although there are people that build platforms like this, ETH Zurich included, there's a lot of interest in just putting the data out there. So, of course, Chicago is up and underway with a dozen or so going to 500. We've got 10 nodes going up in Denver. The first one went up in December. First one was delivered to Seattle just about a week ago. Each of these red ones are projects that we want to do this first half of 2017. The blue ones we're working out for the latter half, and then these other ones are coming in about 1 or 2 per week of groups that are interested. And ultimately, what we want to do is to give back to this community a set of measurements of different cities that is done in a reasonably consistent way, so that folks that are looking at, say, traffic policies to improve air quality on neighborhoods can look at air quality in neighborhoods across these different cities of different sizes, different cultures, different climates, et cetera. So I'll stop there. I think I'm probably close to my time and take some questions.
Thank you, Charlie. Exciting stuff. You are doing the kind of things that we are doing, but you're moving much faster than we are. We're still working on those individual components. So
I did have Hong Kong on the map.
Oh, you do? Okay. So we should sit down.
We should work that out.
We should sit down and work it out. Okay. So now I would like to open up the floor for discussion and questions. Okay. Yes.
It's a pity you miss our talk. We have a mobile equivalent to your system, mobile one.
Yeah.
And we adapt a different approach of modularized things, so you can plug and play, and then replace. And I would like to ask a very technical question about calibrations, because these more sensors, they come in very different quality, and you have to recalibrate them initially and in the middle of their lifetime. And I wonder how you handle this very technical question. Climbing up there and recalibrate them is a difficult job.
Yeah, so some of the sensors should do okay over a long period of time, the standard vibration, temperature, et cetera, because of the technology. Those should do okay. The particle sensor from the US EPA will also do fairly well over time. The gas sensors, those 7 different gases that we're sensing, those are new electrochemical sensors that I think we'll be pleasantly surprised if we're still getting good data from them a year from now. So those will not probably last 2 years. We are talking with sensor vendors about new technologies coming out. Bosch, for example, has a new sensor that, under non-disclosure, we've been looking at. So we think that the problem of sensor lifetime will be less of a concern over time, but it is a concern for some of the sensors we have, for sure.
Professor Catlett, thank you for sharing your experience. Actually, we in Hong Kong, we are cooperating with IOFC in developing the permanent environmental and meteorological devices as well as portable ones. But what we are using is the Arduino-based hardware. I wonder whether you have considered that, because it's available on the market and is relatively cheap. But we do face the problem in using this the hardware, because for some component it will stop supply for a few years' time. And another one is the calibration issue. And especially for the monitoring of gases or the particulate. I have some experience in the observatory, because I did involve in a project in monitoring the air particulate. And if we are using the relatively cheap market available one, which in comparison with professional ones, there are going to be some real problem, and especially of the concerning about the calibration issue. So we have to permanently fix the sensor on the pole, and then it's really a problem if we need to frequently calibrate. But at this moment, we don't know how to tackle this kind of problem.
Yeah, so those are two really good questions. Let me talk about Arduinos and then talk about calibration and lifespan. We did look at Arduinos. We looked at Raspberry Pi, BeagleBone Black. There are a number of different technologies we looked at. We wanted to be able to support a Linux operating system, so the Arduino doesn't support that. It's a very simple device, and we used them a lot in other projects, not in this one here. Raspberry Pi is probably the closest to this. The Raspberry Pi is $30 to $35 US. The devices we're using are like $65 US. So, in the total cost of what we're putting on the pole of about $2,000, about $800 of that are the air quality sensors. $1,200 is the base. So paying $35 versus $65 doesn't have a big impact on the price, but it gives us that important second storage capability. So 2 separate memory systems that we've found to be essential to keep these reliable. Calibration, part of what we're doing here, I've actually said to people, after we get 500 of these up, the most valuable part of the project will be 500 places to plug stuff in across the city of Chicago, not the box that we put up there in January of 2017 or 2018. And the design so that the city electricians can go out and swap these out in 15 minutes means that if it costs me $200 per pole to replace it, then it's feasible to go out and take a different approach, which says, no, we're not going to calibrate every year. We're going to replace every year. So we're really going for a platform, and in some sense, the sensors that we're using today are the least interesting part of the project. It's really about that mechanism for pushing new sensors out there. I should also mention, while we're going to the next question, all the data from this project is open and free. And so these are reporting data about twice a minute, every 30 seconds, reporting all their data, and it will be stored in a number of different places. It's an open API. The Planario system that I showed you that looked for food safety inspections across the part of the city, that's one of the places we'll have the data, and already the APIs for sensor data are documented at the site and usable. We just haven't started to put the data in yet, but it'll be free and open data. Yes?
Yeah, thank you for the talk, and your instrument looks amazing. And many different parameters can be observed, but they have different sensitivity at different height. Like for air quality or the temperature, you hope to observe close to the surface. But if you want to monitor the air traffic or some human being activities, you hope to put it as high as enough so you can see more space. So how do you make the balance, how high you want to put your instrument?
Thank you. These first ones are going 22 feet up. And we're a bit concerned about some of the air quality measures that high up. We've talked to people that look at urban temperature and heat, and they tell us there's probably not going to be a big change in temperature going up and down like that. But we're looking at different ways to just experiment with how good the data can be at 22 feet and which ones of these parameters we need to worry about. In a couple of ways. One, by going out with very good handheld and just going underneath the pole and doing some measurements, kind of sampling. Another is the two of the boards that we're using, the gas sensor board and the board that has vibration and other things. Those two, we've done the engineering with the Big Belly Solar Trash Can Company and with Sidewalk Labs for their kiosks that they're doing in New York City and soon London, as I'm told, so that our boards can slide into their devices, and that would be, in the case of the Big Belly, about 4 feet off the ground. In the case of the kiosks, about 6 feet off the ground. So that's part of the experiment, is to look at heights. And we will also put some of these down at 7 feet off the ground so that nobody bumps their head. And if they get vandalized or stolen, that's part of what we're here to learn, is that'll be just an interesting research result.
Thanks for this detailed talk about your baby project. I just want to know your long-term goal for this project. You mentioned that you will go back to NFC to more funding, replace the existing sensors. But my understanding is the sensors covered its neighborhood. And when you determine the first batch of the location choice, you consider 3 indicators. But would it be long-term goal to build up a census web for the whole city, cover more neighborhood of the Chicago? If that's the case, would you seek more funding and deploy these sensors in a more strategical location?
Well, we have funding in hand for 500 and an agreement with the city to do those 500 installations. And that will take us the next 2 years to do. Chicago is 600 square kilometers, so you could do a uniform distribution. You wouldn't, because it wouldn't make sense, but that's 1 per square kilometer, roughly. The way that we're putting them in is in clusters for specific experiments, and that shouldn't cover the whole city with only 500, but it'll be a very good start. The project is funded through a program that the National Science Foundation runs every year called Major Research Instrumentation. And that is a program that is meant to fund an instrument, or in our case, the development of a new kind of instrument. And the National Science Foundation expects from successful projects to be given a proposal for operating that instrument. So NSF has invested it's a $3.1 million grant. So they've invested $3.1 million for us to build this instrument. And so they're interested in our success and funding the operation of that instrument over time. That also went into the design because we wanted to design an instrument that was cost effective to operate. So when we went with the communication strategy, we had a partnership that we did with AT&T to get essentially wholesale data rates so that it wouldn't be cost prohibitive to do the communication. And our operational proposal, we will, as I mentioned, we'll put in a proposal to operate the existing 500, but also to put new devices in. Those new devices could go in new locations, or they could replace existing ones. I'll just mention, since I talked about networking, the images and the sound will typically not leave the device. They'll be analyzed within the device, and features will be extracted, and that will be sent back. If we were sending these high-resolution images from 2 cameras times 500, that would be very expensive. But we're not sending video or high-resolution. We are sending some for calibration and training images and training sound clips, but most of it is not getting transmitted.
Charlie, maybe on the softer side, okay, I would just like to learn from you how you can get the government, the private sector, and the university together to work on one single project, because this institutional thing is always a difficult thing to crack, when you do a project like this. So any experience that we can learn from it?
Well, it started with the city, and we, over a period of several months, actually several years, worked with the city to envision this project, but from the point of view of the mayor's office. What would this project bring to the city of Chicago? And we had a number of different aspects of the project that we talked to the mayor about. So one of them, obviously, was the mayor was interested in getting data that he wasn't getting already and being proactive about that data. For example, to get data about noise increasing in a neighborhood so that you could act before complaints start coming in. It's a particular interest, a strong interest with the City of Chicago government to not use humans as air quality sensors and say, oh, lots of asthma cases, so we have an air quality problem. So they were very interested in using electronics rather than humans as sensors. We also talked about education, and already the project has caused some interest on the part, especially of undergraduates and high school students. And we've developed a curriculum with one of the local high schools around education. And mayors, I think in Chicago and other cities, mayors are very interested in jobs, and jobs, creating jobs. And so we said, look, if we have this infrastructure for experimentation, then any company that wants to experiment with a smart city technology could come in and work with us to do an experiment in Chicago. That means that they might hire engineers to come live and work and pay taxes and buy things in Chicago. So we started by going to the mayor and saying, first of all, we're responding to a need from the science community, but it's also a need from people in the city. As far as companies go, we essentially said we have in-kind cost sharing from 7 companies, not cash, but engineering help. And we said, look, this is an opportunity for you to work with us and the city of Chicago to learn what might make for a successful or not successful smart city project. And all you got to do is put some engineers, and you can sit in on all of our meetings and work with us. So.
Just 2 points. One, mentioning that we have an educational program for this thing, the co-win. We have over 100 schools participating in putting up the sensors in the school, collecting with Hong Kong Observatory and Poly University. The second is a technical question for you. Have you ever contemplate or anticipate the application of real-time application using your device, like local traffic control for the traffic lights and other real-time applications?
We have thought about real-time research that could be done. Controlling traffic lights is one. Related to that would be controlling traffic lights for specific use cases. One would be lots of pedestrians, not many vehicles, to time the lights differently, longer walk signal, for example. And that's really a public safety issue, and I walk through the city a lot, and I have often been on a street corner with several hundred other walkers, and we're waiting for one car to come because the light's not the right color, and people will walk across, and a certain number of those will get hit by cars. Another is that, I don't think you have this problem here, but we occasionally get ice on the street, and so you would want to look for conditions where the streets are slick and extend the amount of time between when this light turns red and this light turns green. So we've thought about some of those things more than that. With each of those ideas, and when we've talked to science people about these projects, we've just tried to build as flexible a platform as we can so that projects we might not have thought of could be done. But that real time is one of the reasons we made sure that there was an open computing platform, Linux platform there. I think there's a question up here.
Is the city of Chicago already using your sensors for any application other than the crime mapping and projections? And secondly, what kind of a little bit more on the computational side, as on the title of your talk, what kind of computational or modeling type of methods are you employing? Are you adding to the project? Thank you.
So on the first question, the city's not using the data because we're not giving it to them yet. My best estimate is that sometime in the next 3 to 4 weeks, we'll start to give them data from these first units that go up. But I think it will probably be 6 to 12 months before there's enough data there for the city to be interested. So the second question was about computation? Yes.
Could you just generally talk a little bit more about that? If there's any aspects to that in the array of things?
In the array of things, there's not a big computational component other than the computer vision piece. And there, we've been concentrating on putting a platform there that supports the general environment that computer vision and computer listening people use. So for computer vision, and things like the deep learning platform like Berkeley Cafe. The platform's there. It's a small group at Argonne that are doing some of that work. But our next step is in the spring of this year, probably in the April-May timeframe, and we're going to have a workshop where we're inviting computer vision research people to come to Chicago and work with us to look at how they can use these platforms. So we have a small group that's doing that, but we really we see this as an instrument for a broader science community that's certainly at least US-wide, if not worldwide as well.
Thank you.
If you go to the website, just to your question as well, we have published several things that might be useful for other cities already. One is all of our governance and privacy policies are there on the website. And those were done in a very public way with public meetings in the city, online comment capabilities, and in-person comments. And then there's a report on our public engagement that was done by one of our civic engagement partners on all the things that we went through to engage the public on those policies. And then the third thing that's there is for every normative comment or concern or question that we got from those public interactions, we have documented a response to all of those.
Okay, thank you very much for the very useful information. So I would like to thank Mr. Charlie Catlett for the interesting and inspiring talk. Yeah, thanks.